Hello, today I would like to talk about the main issues of the Hudson Yards project. First, I will explain the construction of the deck, which is an important part of Hudson Yards. Next, I will talk about 15 Hudson Yards and the shed. There are four main issues related to the deck. The first issue is the lack of ground for the foundation. The Hudson Yards site was originally the Long Island Railroad, which is LIRR train yard, so buildings has to be constructed above active trains and tracks. As a result, it was not possible to perform basic foundation work such as driving concrete piles into the ground. Therefore, it was necessary to design a support structure for the platform. This involved driving more than 300 piles into the ground, with precise control over their position and angle. Moreover, the columns supporting the platform had to be accurately placed in the empty spaces between the tracks, so ultra-precise design and construction were required. The next issue was bearing the load of the high-rise buildings that would be constructed on top of the deck. A super tall building was planned to be constructed on top of the deck, and if the structure failed to bear the load of the building, it could lead to a catastrophic disaster, similar to the collapse of the Samsung department store in South Korea. Therefore, it was essential to consider methods to distribute the weight of the building in order to address this issue. The third issue was securing a proper ventilation and exhaust system. Covering the rail yard with a platform would trap exhaust fumes and heat inside. Temperatures inside the rail yard could rise up to 150 degrees Fahrenheit, making internal heat exchange and ventilation a critical concern. The final issue was drainage. As many people can easily understand from experience, any rainwater infiltration or leakage between the rail yard and platform could directly affect the ground railway. Therefore, a perfect drainage system had to be designed, and measures to handle heavy rain or flooding also need to be considered. Do you remember the first two issues explained at the beginning of the video? Only 38% of the Hudson Yards site has solid ground, while the remaining area was occupied by the rail yard. Therefore, a deep foundation structure was necessary to safely support the building loads. First, holes were drilled down to the bedrock at depths of up to 40 to 50 meters, and columns filled with steel and concrete were installed. Through caissons, the building loads were directly transferred to the solid bedrock to ensure structural stability. Here, caissons refer to deep foundation structures. Additionally, in certain areas, extra piles were installed to reinforce the weak ground. Moreover, to avoid disrupting train operations, columns had to be installed precisely between the train tracks, which required highly precise construction techniques. The east deck platform was designed like a massive bridge, with a total of 16 steel girder structures installed to perform its basic framework. To carry out this construction, a main tower 18,000 crane was used to assemble the steel trusses in the air. To build the deck, massive steel bridge girders had to be installed, each measuring approximately 100 meters in length, weighing between 800 to 1,200 tons. These girders were assembled in the air using cranes, and then positioned over the rail yard. To ensure structural stability, additional steel trusses were reinforced on top of the girders, preventing the building loads from being directly transferred to the railway facilities. Finally, precast concrete panels were installed over the steel structure, followed by concrete pouring and reinforced work. The third issue, enclosed space beneath the platform structure required a ventilation system. To solve this, large ventilation fans were installed under the deck to bring in fresh air and expel heat and exhaust fumes. An air filtration system was also added to minimize pollutants emitted from the rail cars. Additionally, since a park is located on top of the deck, a sophisticated tubing network was designed to circulate cooling liquid, protecting the roots of the plants from the heat below. Holes were also incorporated in the platform structure itself to allow for natural airflow and ventilation. Additionally, ducts were strategically placed between the platform and the buildings to enable effective air circulation. Smart sensors were installed throughout the rail yard to enable real-time air quality monitoring. Based on the collected data, the operation levels of the ventilation system could be adjusted and alerts were set to trigger when air quality reached hazard levels. Now, the final issue, drainage, had to be addressed. To solve this, the surface of the deck was designed with a slight slope to allow rainwater to flow naturally. Drainage channels and drains were strategically placed at key locations to quickly discharge water. A drainage system was also constructed underground. Waterproof layers and drainage pipes were installed between the platform and the rail yard to ensure smooth water flow and effective drainage. During heavy rain, a stormwater discharge system was applied to prevent water from directly entering the railway facilities. Finally, rainwater falling on the Hudson Yards public plaza was collected in a 60,000-gallon tank and reused for irrigating plants and trees. By collecting and reusing this water, the project was able to save 6.5 megawatt-hours of energy annually and offset 5 tons of greenhouse gas emissions. As a result of utilizing this drainage system, the deck was able to prevent flooding of the rail yard even during heavy rainfall, ensuring that the underground facility remained safe and secure. Now, let me talk about the foundation of 15 Hudson Yards. 15 Hudson Yards installed a slurry wall to block groundwater infiltration and stabilize the ground. The slurry wall method addresses the issues of noise and vibration pollution often associated with traditional or retaining wall construction. Slurry wall construction process involves guide wall installation, preliminary excavation using a hand grab, excavation with a rotary excavator while injecting stabilizing fluid, rebar cage fabrication and placement, trimming pipe installation, concrete pouring while recovering the stabilizing fluid, trimming pipe removal, and finally, cap beam installations. In addition, to avoid the railway tracks and install deep foundation in narrow spaces, a pile method was used to safely transfer foundation loads down the bedrock. This is known as micro-pile construction. Its features include the ability to work in confined and restricted areas using small equipment, securing shear deformation and symmetric loads with high-strength steel bars, adaptability in narrow spaces through cutting and coupler connections, and ease of incline installation from any angle. Finally, the platform was constructed with steel trusses and a concrete deck over the tracks, and 15 Hudson Yards was connected to the joint section of this platform using foundation anchors. Next, let me talk about the construction of 15 Hudson Yards. 15 Hudson Yards was constructed using a hybrid structure system. The lower part of the building was built with a concrete core wall to ensure stability, while the upper part used a steel frame to reduce the weight of the high-rise section and improve construction speed. This method effectively distributes vertical loads and lateral forces while also optimizing the construction sequence. The exterior of the building was constructed with a curved curtain wall, creating an aesthetically pleasing design. Each glass panel had a unique curvature and size, so all panels were custom-made. Finally, our team's main building, the shed. The most distinctive feature of the shed is its movable outer shell, which operates on a rail system. Therefore, a foundation capable of absorbing the vibration and shocks caused by the moving outer shell was required. The foundation was first constructed based on static load conditions, followed by reinforced design that accounted for dynamic loads. Unlike static loads, dynamic loads are difficult to predict, so it is crucial to fully consider them during structure design. This includes establishing plans for elasticity, vibration resistance, and fatigue design to ensure the structure can withstand varying dynamic forces effectively. Therefore, damping materials and vibration isolation systems were installed within the foundation. Since the structure had to support the rails and wheels without deformation, high-performance concrete and reinforced materials were used. Now that the foundation of the shed has been completed, let's take a look at the method used to construct its outer shell. The outer shell structure, weighing approximately 2,000 tons, was assembled on the ground and lifted using a crane. The shell moves along rails using an 8-wheel system, and special protective equipment was used during construction to prevent damage to the rail. The outer shell was made with ETFE film, which was inflated and fixed on site. The walls, floors, and ceiling of the exhibition space inside the performance hall were constructed using a modular system, allowing for easy disassembly and rearrangement when needed. The diamond-shaped metal frame supports a state-of-the-art floor designed for theatrical performances up to 35 meters in height, and it also provides lateral support for the ETFE outer shell, which must withstand strong winds blowing through the densely built-up area of Manhattan. This type of structure is called a die-grid structure. When wind strikes the building, the diamond-shaped grid alternates between tension and compression forces to resist the impact. This design significantly enhances the building's ability to withstand typhoons, earthquakes, and other external forces. That concludes my presentation, and I will now show our team's future plans. Thank you.